Yeah, hi, we continue our lecture. Okay, so last part, we stop at here, at this slide. Okay, for the parallactic angle. Now we go to the seeing. Okay, so what is seeing? Talk about is the effects of the Earth's atmosphere on the visible image of astronomical object. Okay, so the telescopic image of stars exhibit variations in the intensity or scintillation. We use term in scintillation for intensity and sharpness for the blurring. Okay, and position for the image motion. So these three effects correlate with each other and have a common cause. Okay, so but in our context, seeing only includes image blurring and motion. So not including the intensity scintillation. Okay, so we may describe this effect in terms of two modes of observation. So we have a telescope with aperture less than 5 inch and telescope with aperture more than 20 inch. Okay, so for a small telescope less than 5 inch, there is a rapid movement of the star's image, and the angle through which the image appears to move is found to be 2.5 on a night of average seeing. Okay, for the large telescope, more than 20 inch, there is rapid change in size and shape. Okay, so for the small telescope, rapid movement of the star's image. Okay, so you have to note about their keyword for any particular telescope. For the small telescope is the rapid movement of the stars. For the large telescope is the rapid changes in size and shape. So the average appearance of the image creates of a seeing disc. Its size can range 1 to 10 inch. So a star's diffraction disk can be seen if the seeing condition is good. Okay, a related observation, okay, for the medium-sized telescope on any clear night, point the telescope toward a bright star, remove the eyepiece, look directly at the mirror or lens, observe a rapidly moving pattern of irregular dark bands on the objective, having a transverse velocity of the wind. So these 4 points are important for the observation using medium-sized telescope. So a similar effect is the shadow bands seen just before and after a solar eclipse, patterns of light and dark moving up to 10 km per hour. So seeing is caused by small scale variations in the index of refraction of the air. Okay, so let's see here. Okay, the diffraction that occurs when light passing through the refractive index of air or cell of air. Okay, so there is extensive mixing of air of different temperature coming from range of height, causing the variation in refractive index. Okay, so the volumes of air of differing refractive index can be imagined to be a layer of lens-like cells, so very thin. Parallel rays entering this moving cell will be refracted to produce pattern of light and shadow moving in a certain direction. Okay, for a small telescope, it's not as large as the size of the projected cell, yeah, dia punya aperture. Okay, so rays of light entering the telescope come through only a part of one cell. Okay, so the direction in which the rays enter the small telescope is continually changing. So the star's image move in the focal plane. Okay, for large telescope, the rays, okay, the rays falling on the lens, right, or mirror have passed through a number of adjacent cells. So the rays are not parallel, producing a large blur image. Okay, so that is how the rays are come or pass through the atmosphere, or the A for the small and the large telescope. Okay, so let's see the formula which related to the seeing. Okay, so S is equals to S naught. S naught is the seeing at the zenith. Okay, zenith location, position. Okay, and X is ms. Okay, to the power of 3 over 5. So observation should be made at low air mass if sharp image are desired. Okay. Measurement of the atmosphere show that much of the seeing is caused by turbulence at about 7 kilometer altitude. Seeing problems can also originate much closer to the observer. Okay, for example, prevailing winds. Okay, now we go to isolated peak. Okay, isolated peak is a good site since the moving air masses could move around the peak. Okay, however, on still last night at hilltop observation, cold air could settle into the valleys and slowly push a layer of warmer air upward, causing bad seeing. Okay, this is the description for the bad seeing. Okay, okay, for the dome seeing, okay, caused by the air flowing around a telescope's dome. Okay, if you have this dome, okay, this kind of dome. So actually the air flowing around a telescope dome, okay, this one, and the temperature different between its interior and exterior. So the temperature in the interior and exterior is also contributed to the dome seeing if you want to do the observation in the dome area. Okay. Okay, this one is a diagram, the picture. Okay, I don't know where it is taken. Dome seeing can be mitigated by allowing airflow in the dome. Okay, so for example, you have to open the dome at sunset, adding louvers to the observatory, adding exhaust fans, okay, removing heat sources, changing shape of dome, and so on. Okay, maybe the dome you can have open air from here, or maybe next day you open and on the other side. Okay, so there a moving of air, okay, coming through from the exterior to the interior, interior to the exterior. The scene can be monitored with a small telescope equipped with a CCD camera, monitoring the separation of two images of a star from a double beam telescope. Okay, now we go to scintillation. Okay, what is the scintillation? Is the variation in brightness of the object when seen through a medium. Twinkling or visual scintillation is usually seen as rapid fluctuations. Okay, fluctuations. This one. Okay, fluctuation in the brightness. Okay, fluctuation in their in term of their brightness of stars seen with unaided eye. So when stars are seen close to the horizon, they also seem to undergo rapid changes in color. Twinkling is not constant every night. It happens lesser at high elevations, and planets do not twinkle to the degree that stars do. Okay, so normally we will see in the night sky, we will see a star twinkle. Okay, a star twinkle, but not for the planet. Planet is uh, commonly not undergoes the rapid changes in color. Twinkling correlates inversely with angular size. For example, Mars shows more scintillation than Venus. So the twinkling is about the fluctuation in the brightness. Okay, in reality, scintillation increases as angular size decrease. Okay, and suggesting to be the mean angular size of an individual cell of turbulent air. Okay, so you have here measured from balloon borne telescope. Okay, high turbulent layer causing scintillation, and for high altitude wind, turbulence, integration time, and telescope aperture. Okay, okay. Now we see the equation, the Andrew Young equation. Okay, it's quite complex equation. We have exponent here, and what is D? D is the aperture. X is the ms, lambda wavelength, h elevation, h here, and m. Where is m? Above sea level. H is the elevation. Okay, yeah. M is the height, height of the sea level, and T is the integration time s, second. So destination noise for a T equals to 10 second with a 1 meter telescope. Okay. So dia punya this one dia punya scintillation noise. Okay, this one is the scintillation noise. Scintillation noise is at 1.7 mmAg. So they calculate this by using this information. We substitute in this formula. Okay. Okay, so for the precise value of the exponent of the ms depends on the wind direction. Okay, so you have it is x squared when observing in the same direction as the wind, and it is x equals to 5 over 2. Power of 5 over 2 when observing perpendicular to it. So in the same direction, this one for perpendicular. Okay, so to minimize scintillation noise, okay, to minimize this one scintillation noise, an observer should strive to use a large telescope, observe at high observatory, use a red band pass, observe object near the zenith, point the telescope perpendicular to the wind direction, okay, perpendicular to the wind direction, and use long integration time. Okay, for example, we have this figure, okay. The calculated scintillation noise is too small by a factor of 2 to 3 since we expect scintillation to be the dominant noise source of the data. So this is the scintillation noise. Okay. Scintillation noise. Okay, so photometric uncertainty. So they calculate mm, scintillation noise. So they found out the fluctuated pattern. So in practice, the equation should be calibrated with observation made at the start of an observing run. Okay, so we go to the dispersion. Okay, dispersion is the splitting of light into its component wavelength during refraction. So example for atmospheric dispersion, we have the rainbow, okay, rainbow phenomena, chromatic twinkling, and the green flash. When a telescope is pointing on a planet or a bright star, okay, the image may appear like a miniature rainbow stretched along an altitude circle with red closest to the horizon. As a star strikes around across the sky, its dispersed spectrum will appear to rotate in the field of equatorial mounted telescope as much as the parallactic angle. Okay, we have learned about the parallactic angle before. At the zenith distance of 60 degree, atmospheric dispersion causes the blue and red image of a star to be separated. Okay, so the apparent relative position of the star will depend on its colors. Okay, so blue stars are shifted closer to zenith than red star. Okay, this color dependent shift can be minimized by avoiding the use of broadband filters, and can also be corrected with a prism for moderate zenith distance. Okay, this one is for the correcting for the atmosphere. Okay, I will continue this lecture for the in the next video. Okay, thank you.